In March of 2025, a team of scientists ended a search that had lasted more than 3 decades without success. They were looking for something that, by every theoretical prediction, should have been easy to find. A specific, telltale molecule glowing faintly in the upper atmosphere of Neptune, proof that the most distant major planet in our solar system has auroras, just like every other giant planet does. Astronomers had already confirmed auroras on Jupiter, Saturn, and Uranus decades earlier. Neptune was the one holdout, the missing piece of the puzzle, and despite repeated attempts using some of the largest, most powerful telescopes ever built on Earth, it stayed hidden. Then, when the James Webb Space Telescope finally found it, the confirmation came bundled with a second discovery nobody had gone looking for at all. Neptune's upper atmosphere has cooled by hundreds of degrees since the last time anyone measured it directly, and right now in 2026, scientists still don't have a confirmed explanation for why. This is the story of what the James Webb Space Telescope has revealed about Neptune since it first turned its instruments toward the planet in 2022, why one of its most striking early images ended a 33-year wait to see Neptune's rings clearly again, and why a newer discovery about the planet's auroras has left researchers with a genuine, still open mystery about a world nearly 3 billion miles from the Sun. To understand why Webb's observations of Neptune carry so much scientific weight, you first have to understand just how little direct information we've ever actually had about this particular planet, and why that scarcity made every new observation count for so much. Neptune is the outermost of the 8 recognized planets in our solar system, orbiting the Sun at an average distance of roughly 8 billion miles, so far out that it takes about 165 Earth years to complete a single orbit. Because of that extraordinary distance, and because no spacecraft has ever been sent there on a dedicated mission, almost everything we know about Neptune traces back to a single event, a brief flyby by NASA's Voyager 2 spacecraft on August 25th, 1989, the only time any spacecraft from Earth has ever passed close enough to study the planet directly. In the roughly 36 years since that flyby, our understanding of Neptune has depended almost entirely on what Voyager 2 measured during that one encounter, supplemented by whatever ground-based telescopes and Earth-orbiting observatories like Hubble have managed to observe from a distance in the decades since. That's precisely the gap the James Webb Space Telescope has begun to fill, and it started doing so almost immediately after becoming fully operational. On July 12, 2022, NASA released one of Webb's first major images of Neptune, and it did something no telescope had managed to do since Voyager 2's flyby 33 years earlier. It showed Neptune's rings with genuine clarity. Neptune's ring system is faint, dusty, and difficult to observe, made up of several narrow, distinct rings named after astronomers who contributed to the planet's discovery and study, including the Adams and Leverrier rings, along with fainter dust bands in between. Because these rings are composed largely of dark, dust-sized particles rather than the bright, icy material that makes Saturn's rings so easy to see, they had proven remarkably difficult to observe clearly from Earth in the decades since Voyager 2 first photographed them up close. Webb's near-infrared camera, sensitive to exactly the kind of faint infrared glow these dusty rings reflect, captured them in crisp, clean detail, along with several of Neptune's smaller moons, providing astronomers their best look at this ring system in over 3 decades. That image alone would have been a meaningful achievement. But it turned out to be just the beginning of what Webb was capable of revealing about Neptune, because a year later, in June of 2023, a research team turned a different one of Webb's instruments toward the planet, specifically hunting for something that had eluded every previous attempt to find it. The instrument used was Webb's near-infrared spectrograph, commonly abbreviated NIR-SPEC, a tool built not to simply photograph an object, but to break down the light coming from it into its precise component wavelengths, revealing the specific chemical fingerprints of whatever molecules are present. The target of that particular search was a molecule called trihydrogen cation, abbreviated H3+, a specific ionized form of hydrogen that forms in the upper atmospheres of gas giant planets, specifically as a byproduct of auroral activity, the same basic phenomenon responsible for the shimmering northern and southern lights here on Earth, produced when energetic, charged particles, usually originating from the Sun, become trapped by a planet's magnetic field and funneled down into its atmosphere, where they collide with and excite atmospheric molecules, causing them to glow. By the early 2020s, astronomers had already confirmed this same H3+ signature, and the auroral activity it represents on Jupiter, Saturn, and Uranus, each one detected and studied years, in some cases decades earlier. Neptune remained the conspicuous exception, the one giant planet in our solar system where this expected, theoretically predicted signature had simply never been found, despite what researchers describe as genuinely persistent effort. As Heidi Hamel, an astronomer with the Association of Universities for Research in Astronomy who has studied Neptune for decades, explained in comments included in NASA's official announcement of the discovery, H3 Plus has been a clear signifier on all the other gas giants of auroral activity, and researchers had fully expected to find the same signature on Neptune as they investigated the planet over the years, using the best ground-based facilities available at the time, including Hawaii's Keck Observatory and NASA's own infrared telescope facility. Those repeated attempts consistently came up empty. Only with an instrument as sensitive as Webb, Hamill noted, did astronomers finally get the confirmation they'd been chasing for so long. The results of that 2023 observation were formally published in the journal Nature Astronomy on March 26, 2025, in a paper led by Henrik Mellin, a planetary scientist at Northumbria University in the United Kingdom, alongside co-authors including Leah Fletcher of the University of Leicester, Stephanie Milam of NASA's Goddard Space Flight Center, and James O'Donoghue of the University of Reading. Mellin, describing his own reaction to finally seeing confirmed evidence of Neptune's long, elusive auroras, said in a statement accompanying the publication that it was so stunning not just to see the auroras themselves, but the sheer detail and clarity of the signature, which genuinely shocked him. O'Donoghue offered a similarly direct reflection on just how long this particular search had dragged on, noting that nobody had actually seen Neptune's auroras since 1989, despite the research team's best efforts using the world's largest telescopes, calling it, in his own words, a real head-scratcher, one finally resolved thanks specifically to the sensitivity of the James Webb Space Telescope. Why had this particular signature proven so stubbornly difficult to find when the same basic phenomenon had already been confirmed on 3 other giant planets years earlier? The answer, once Webb's data made it clear, turned out to involve 2 separate compounding factors, one already known and one that emerged as a genuine surprise once the new observations were fully analyzed. The already known factor involves Neptune's magnetic field, which behaves in a genuinely unusual way compared to nearly every other magnetized planet in the solar system. Voyager 2's 1989 flyby had already revealed that Neptune's magnetic field is tilted by approximately 47 degrees relative to the planet's rotational axis, an extraordinarily large offset compared to Earth's own magnetic field, which sits misaligned from our planet's rotational axis by only about 10 degrees. Because auroras form specifically where a planet's magnetic field lines converge and funnel charged particles down into the atmosphere, and because Neptune's magnetic field is tilted so dramatically relative to its spin axis, its auroras don't appear near the planet's geographic poles the way Earth's and most other planets typically do. Instead, according to NASA's own description of the findings, Neptune's auroras occur at mid-latitudes, roughly analogous to where South America sits on Earth's globe, a genuinely unusual, off-kilter location that made searching for them considerably more difficult than simply pointing an instrument at the planet's poles the way researchers might for Jupiter, Saturn, or Uranus. The geographic quirk alone helps explain part of why Neptune's auroras proved so elusive for so long, but it doesn't fully explain the difficulty. And this is where Webb's June 2023 observations revealed something researchers hadn't specifically gone looking for, a second, genuinely unexpected finding layered directly on top of the aurora confirmation itself. Alongside detecting the H3 Plus signature confirming Neptune's auroras, Webb's near-infrared spectrograph also allowed researchers, for the first time since Voyager 2's flyby in 1989, to directly measure the actual temperature of Neptune's upper atmosphere. What they found was, in the words of multiple researchers involved in the study, genuinely surprising. According to the published findings, Neptune's upper atmospheric temperature has dropped dramatically since 1989, with the planet's atmosphere in 2023 measuring at just over half the temperature Voyager 2 recorded during its flyby more than 3 decades earlier, a difference amounting to several hundred degrees Fahrenheit. That cooling turned out to be directly connected to why Neptune's auroras had remained so difficult to detect in the first place, providing the second half of the explanation researchers had been missing. Because the strength and visibility of auroral activity is directly tied to atmospheric temperature, with warmer upper atmospheres generally producing brighter, more easily detectable auroras, and colder atmospheres producing considerably fainter ones, Neptune's substantial cooling since 1989 meant its auroras had likely become significantly dimmer and harder to spot than they may have been at the time of Voyager 2's original flyby, compounding the already existing challenge posed by their unusual off-pole location. That explains why the auroras were so hard to find. It does not explain why Neptune's atmosphere cooled so dramatically in the first place. And this is the part of the discovery that remains, as of 2026, a genuinely open scientific question rather than a solved one. As reporting on the findings from the Smithsonian Magazine put it directly, the data revealed a new mystery. While the temperature drop helps explain the difficulty in observing the auroras, it doesn't explain why the ice giant cooled so dramatically in the first place, an answer researchers have suggested might only emerge through further study and continued observation. It's worth taking a moment to understand exactly why this temperature drop is considered so genuinely puzzling by the scientists studying it, rather than simply an unremarkable expected fluctuation. Neptune sits more than 30 times farther from the Sun than Earth does, and completes a single orbit only once every 165 years. Given that enormous distance and correspondingly enormous orbital period, the kind of seasonal temperature variation familiar to us here on Earth, driven by the changing angle of sunlight reaching different parts of our planet throughout a single one-year orbit, would be expected to play out on Neptune across a vastly longer timescale, with any given season on Neptune lasting decades rather than months. A meaningful atmospheric cooling event playing out over the roughly 3.5 decades separating Voyager 2's flyby from Webb's newer observations represents a genuinely unusual rapid shift, one that doesn't fit neatly within the kind of slow, predictable seasonal cycle you might otherwise expect from a planet orbiting so far from the Sun over such an extraordinarily long year. Researchers involved in the study haven't proposed a single confirmed explanation for the cooling, and it's worth being direct about that uncertainty rather than glossing over it. What they have proposed is a path toward eventually resolving the question: continued, sustained observation of Neptune using Webb over an extended period of time, ideally spanning a substantial portion of the Sun's own roughly 11-year activity cycle, since solar activity levels are already known to influence conditions in the upper atmospheres of giant planets throughout the solar system. According to NASA's own description of the team's future plans, astronomers intend to continue using Webb specifically to investigate Neptune's magnetic field and atmospheric behavior across that full 11-year solar cycle, gathering the kind of sustained, repeated observations that a single flyby, however historically significant, could never have provided on its own. That plan reflects something genuinely important about how Webb has changed the nature of studying distant planets like Neptune, compared to relying entirely on a single spacecraft flyby that happened over 3 decades ago. Voyager 2's 1989 encounter, however historically significant, offered scientists only a single brief snapshot of Neptune's conditions at one specific moment in time, as the spacecraft sped past at tens of thousands of miles per hour, unable to linger and observe how those conditions might change over subsequent days, months, or years. Webb, positioned in a stable orbit roughly 1 million miles from Earth, can return to observe Neptune repeatedly whenever researchers choose to schedule new observing time, building up exactly the kind of longitudinal, repeated dataset needed to distinguish a genuine ongoing trend from a single isolated anomaly, something no flyby mission could ever hope to accomplish on its own, regardless of how sophisticated its instruments were at the time. There's a broader scientific value to resolving Neptune's temperature mystery that extends well beyond simple curiosity about one distant planet's atmosphere. Neptune belongs to a broader class of planets astronomers call ice giants, a category that also includes Uranus, and one that appears to represent an extremely common type of planet found throughout the broader galaxy, based on the large numbers of similarly sized planets discovered orbiting other stars in recent decades. Understanding exactly how and why an ice giant's atmosphere changes over time, what drives those changes, and how strongly they might be influenced by factors like solar activity, internal heat sources, or longer-term seasonal cycles playing out over multi-decade timescales, has implications reaching well beyond our own solar system, potentially informing how astronomers interpret atmospheric observations of similarly sized ice giant exoplanets discovered around other stars entirely. Planets we'll likely never be able to study with anything approaching the level of direct detail Webb has now made possible for Neptune itself. It's also worth appreciating, honestly, just how significant it is that this entire chapter of Neptune research, the ring image, the aurora conformation, and the temperature mystery all together, has unfolded using a single space telescope observing from nearly 1 million miles away, rather than requiring a dedicated multi-billion-dollar spacecraft mission of the kind that hasn't been sent to Neptune since 1989, and that no space agency currently has firmly funded or scheduled to launch anytime in the near future. Webb's extraordinary sensitivity, particularly in the infrared wavelengths, where both Neptune's faint rings and its auroral H3+ signature happen to be most detectable, has effectively allowed scientists to conduct a level of ongoing, repeated study of this distant, difficult-to-observe planet that would otherwise have required an entirely new dedicated mission, one that, given typical planetary mission timelines and funding cycles, likely wouldn't arrive at Neptune for decades, even under highly optimistic planning scenarios. That's really the through line connecting everything Webb has revealed about Neptune since 2022. A planet nearly 3 billion miles away, visited directly by a spacecraft only once, over 3.5 decades ago, is now, for the first time since that single historic flyby, being studied with genuine, sustained scientific attention, revealing both long-sought confirmations, like the elusive auroras astronomers had specifically predicted should exist there, and entirely unexpected mysteries, like an atmospheric cooling trend that, as of 2026, still doesn't have a confirmed explanation. Both of those outcomes, the confirmation and the mystery, represent exactly the kind of genuine scientific progress that comes from finally having a capable, sustained set of eyes trained on a part of the solar system that had, for over 3 decades, been left to rely almost entirely on a single, brief encounter for nearly everything we thought we understood about it. Neptune sits out there right now, nearly 3 billion miles from the Sun. Its faint, dusty rings and its dim, oddly positioned auroras, both finally captured in genuine detail for the first time in over 3 decades. Its upper atmosphere is still measurably, mysteriously colder than it was when Voyager 2 sped past all those years ago, for reasons researchers are still actively working to understand. If you want to see what continued observations across the coming years of the Sun's own activity cycle eventually reveal about why that cooling happened, and what else Webb might still uncover about this distant, quietly strange ice giant, that story is still being actively written. Subscribe if you'd like to keep following where it goes.